All right, so this time we're doing a calculator for t-tests. This is less of a calculator and just how to use the data analysis tab, really. So really quickly, we're going to go over t-tests very fast. We did this in class, so this is just a quick reminder. But basically what we're doing is we want to see if there's a significant difference between these two groups. There's a couple different ways that we can do this. We have two different kinds of tests. Two different kinds of tests in one, and then like a subgroup in one of those. But one of these is a paired samples t-test. And with a paired samples t-test, what you're looking at is that the observations are tied together somehow. Maybe it's the same person, like perhaps I'm keeping track of my run times between two different time periods, so I'm the same person. Maybe I have a whole bunch of friends that are doing the same thing, but we're only looking at my time to my time, and my friend one's time to friend one's time, friend two's time to friend two's time. Maybe we're doing a pre-test and post-test, so we're seeing if what we've learned in a class is actually teaching us anything. So we take a test before we learn the material, then we take a test after. And we want to only, again, look at how that one person did on the pre-test and the post-test. You can also do a matched control. So maybe you have twins like these guys. A couple of years ago, one of them went to space for a year and the other stayed on Earth. And what they did was they wanted to measure how staying in space that long changes a person. You can't really do that. I mean, you could send anyone to space and you could measure what changed about staying in space for a year. But you wouldn't know how much of that was actually due to just the natural aging process of 1 year of aging and how much of it was actually due to space. It just so happened that these two twins, the Kelly Bros, um, are both astronauts, and so they had physical checkups before one went to space for a year, and then physical checkups after, and so they could kind of use that as sort of the same person. It's a matched control. So any effects of aging are that we see in one twin, the one that remains on Earth, are removed from the data that we gather from the one that went to space, and then we know what is actually the changes caused by space. We could also think about measuring the temperature in the city where you live on the exact same day, 30 years apart. These would be matched controls. It's the same day of year, but the time difference is really what we're measuring. So we don't want to measure the difference between June 1st and January 1st. So we want to match those up, pair them. And so we're looking at June 1st, 1990 and June 1st, 2020. So that's a paired samples t-test. An independent samples t-test is not exactly the opposite, but it doesn't have that constraint. The observations are completely unrelated. I want to compare I want to look at the effect of time of day. Like, am I a more effective teacher in the morning than I am in the afternoon? So what I do is I look at the test scores for those whole classes, the morning class versus the afternoon class. And it doesn't matter. There's nobody that I'm matching anyone up with there. Nobody is just like somebody else. So I can't really do that. So that's an independent samples t-test. This is William C Lee Gossett. He is student. If you've heard of the student's t-test, he made the student's t-test, and basically he made it to see if he could get more yield out of a different strain of barley to make better beer for the Guinness Brewing Company. So definitely the best reason to invent a statistical test is to make more beer. A paired samples t-test removes the unique effects of a person or situation, so you're getting rid of the noise. And the flip side of that would be that the independent samples t-test has more noise because you're not removing all the noisy components. So why do we not always just use paired? Well, it's not always practical. Like, let's say we're looking at surgical procedures. You can't test two different surgical procedures on the same person. You have to do something else. Maybe you could have a matched control, but that's not always possible, so you might just have to compare two different surgical procedures with people that aren't matched with each other. Maybe you're having people run a maze, and the second time they run the maze, they know exactly where they're going. So again, you can't have them run twice. So you just gather a group and you look at their average time. You gather another group that you've done something else to, and you look at their time. Paired samples t-test is kind of the same thing as doing a single sample t on the difference between groups. So you subtract time point 2 from time point 1, and then you just have one string of data. It's the difference score between all of those. And then you can just do a one sample t-test on that data. Is that different from 0? And that's basically what you're doing with a paired samples t-test. Okay, here's the different formulas that we're going to need if you're not using the data analysis tool pack. Let's do data analysis tool pack first, and then we'll come back and build our calculator. So I'm going to go to this Excel sheet here. This is linked in the video. It's also on Canvas if you're one of my students. We're looking at barley yield, good old William C Lee Gossett stuff here. We've got year 1 and year 2. So we're not looking at two different species of barley. We're looking at, this is the same plant. This is plant 1. And this is plant 2. And so on. So really we're just looking at, is there a difference between the two years? That's what we want to know. So this is a paired samples t-test, the same plant each time. All right. So what we're going to do is we're going to go to the data tab. We'll go to data analysis. And we're doing a paired samples t-test, so go ahead and click OK. I've already got this set up, but yours is going to look like this. What you're going to do is in the variable 1 range, you're just going to select all of your stuff in variable 1 for variable 1, including year 1. You want to make sure that you grab the label. For variable 2, you're going to grab the label for year 2, drag it all the way down. And then you need to tell Excel that you have labels. It's very important. If you don't, it's going to think that one of your numbers is year 1, which of course isn't a number, and it's going to have a fit, and all sorts of terrible stuff happens after that. Okay, so you don't need to do anything with hypothesized mean difference. You don't need to do anything with alpha. That's a fine alpha. It's what we're always using, unless there's some reason to change that. So for your output options, you can do output range, and then you can just click in E1 and get your data right there in E1. And that's what I'm going to do. You could also do a new worksheet. You could type in a name here, and it would make a new worksheet down here at the bottom with your results. But I want to keep everything on the same sheet for now, so I want an output range. I want it in E1, and that's it. Okay. So what did we learn here? Well, so here's our means. The mean from year 1 is 38.9. The mean from year 2 is 33.85. These are important things to have. I'm going to highlight those. The variance, this is important to have too. If we're doing a write-up for our results section, we're going to need the means, we're going to need the standard deviations. Excel doesn't give you the standard deviation, but it does give you the variance. And if you remember from earlier in the class, one of the things that you can do to find standard deviation is you can take the variance and find the square root. So you can type in, that's not the right formula, equals, because every formula starts with an equal sign, SQRT, open parenthesis, because after every operation that we type in, every formula, losing the word that I'm trying to say here, but each operation that Excel is going to do that is like a piece of code that it already has in it, an operation that it's going to do, you have an open parenthesis. I'm going to take the square root of this variance here. And there's our standard deviation. We can click on that, go to this fill handle here, and move to the side. And now we've also got the standard deviation for year 2. So we could just write these in. There we go. Observations. Just check this to make sure that you have 20. You know that you should have 20 or however many observations you have with whatever you're working with. This is just good to look at. There's a Pearson correlation. You're not usually looking at that. Hypothesized mean difference we didn't set. Degrees of freedom is something that you're going to need. And you're also going to need the t-stat. And lastly, you're going to need the p-value for the two-tailed test. You're always grabbing two-tailed test unless your homework says otherwise. But in the real world, it's always two-tailed. And you can see that the two-tailed test is just barely not significant. It's 0.06. So we just barely didn't make significance. Okay, so let's look at the independent samples t-test. Well, you can see that this data here, these data are exactly the same. The numbers are identical, but what we're doing with them with the story is a little bit different. Now we're looking at 2 different species of barley. It's not one year and the next, it's 2 different species. We can't say that this is plant 1 of species 1 and this is plant 1 of species 2. That doesn't make sense. They're not linked in any way. So now we're going to do an independent samples t-test. So like before, go to the data tab, go to data analysis, and this time we're going to click on t-test to sample assuming equal variances. If you, and once again I have this already set up and ready to go, sorry about that. If you notice that a variance of one of your groups is twice that of the other, that's when you're going to use unequal variances, but otherwise you're going to use equal variances. So this is going to give you variance. You'll be able to see if one is twice the other. So you might as well start with the equal variances and then go from there. What you're going to do in variable 1 range is you're just going to select from species 1 all the way down. Got to grab that label. It's important and helpful to grab the label. For variable 2, grab species 2 and go all the way down. Make sure that you tell Excel that you have labels. Same reason. It's going to freak out if you don't. And again, you could do a new worksheet. You could do an output range. I'm going to do an output range again. And I'm just going to throw this into cell D1 here. And that's it. It's that simple. Go ahead and click OK. Now remember, I said that these data are identical to what we used for the paired t-test. However, the p-values are very different. What are things we're going to need from this? Well, we're going to need the averages again. We're going to need the variances again. And it actually looks like we should have used the unequal variances t-test here, because this is more than twice of this. So now what we're going to do, it's almost like I set this up in advance, isn't it? So now what we're going to do is go back to the data tab, go to data analysis, and now you're going to choose unequal variances and click OK. Your variable 1 range is the same range, including the label. Your variable 2 range is the same thing, including the label. And you don't have to go from the top. You can go from the bottom. Sometimes that's easier. Remember to tell it you have labels. I'm going to put it in the same worksheet, so I'm going to have it do an output range. I'm going to go into cell H1, and I'm going to click OK. And these are our answers, right? So we need the means, as always. We're going to highlight those. The variances we can turn into standard deviations. We'll need those. Observations, we have 20. Good. Degrees of freedom, you're going to need that. It's 32. Over here was 38. Degrees of freedom of an independent samples t-test is usually n minus 2. N minus 2. We have 20 observations in each group. 20 plus 20 is 40. 40 is our n. Minus 2 is 38. But what we're doing to account for unequal variances here is we're changing the degrees of freedom. And that's why over here it's 32. If you were writing this up for a paper, you'd want to make a note that you use the t-test for unequal variances. People might notice that if you say that you used 40 participants and then you report a DF of 32, that something isn't right. So if you tell them that you did a correction for unequal variances, they'll understand why. Again, we need the t-stat, and we need the p-value for a two-tailed test. Okay. Again, these data, exactly the same as our paired samples t-test. Look at this two-tailed p-value. Look at this two-tailed p-value. It is very different. Also, another thing that you'll notice that's different is the DF for the degrees of freedom for a paired samples t-test is not 38. It's not 20 plus 20 minus 2. It's not n minus 2. It's actually the n of one group minus 1. And the reason for that is because you can kind of think about, like we talked about, you think about this paired t-test as a one sample t for the difference scores between time point 1 and time point 2. You cannot think of the independent samples t-test in the same way. That's a whole different ballgame. You're actually looking at two different groups here. And these are the important things that you're going to need. All right, if you have the data analysis tool pack, you're done. If you don't have the data analysis tool pack and you need to figure out how to make a calculator, that's what we're going to do right now. Okay, so let's look at our formula again. So you can see that this one over here, this is the paired t-test. Now, usually we're used to seeing x1 minus x2 or x bar minus m if we're looking at a one sample t-test, but what we've got here is d bar. What that means is the average of the differences. So we are going to take the difference scores for all these. So you have the difference score here, and then what you're doing is you're dividing the standard deviation of the differences by the square root of the number of observations that you have. So let's go back to Excel. And here's our paired samples t-test. So if you are making a calculator, what you want to do is find the difference scores first. So you're going to make a new column. You can call it diffs. And you're just going to say equals, because you're going to have a mathematical operation here. B3 minus A3. And what we're going to do is we're going to click on that, go to the fill handle where your cursor changes, down here on this little dot in the lower right-hand corner, and drag that all the way down until you are equal with the end of your data down here. So now we have different scores. Good. And one thing that we want to do is we want to find the average and standard deviation of those different scores. So what we're going to do is we're going to type in average and standard deviation. In average, we're going to say equals average, and then open parenthesis, and just select all of these difference values here. And in standard deviation, we're going to say equals, STDEV. Hopefully you remember that from the beginning of class. Open parenthesis and then select all of this data here. Okay, so we have the average is -5. The standard deviation is 11 point, roughly 5, 11.5. And we want to put the n here as well. We have 20 participants. So what we're going to do, take a look at our formula again, is we're going to make the standard error for the one sample t-test. There we go. The standard error for the paired t-test. The standard error for the paired t-test is all of this bottom portion here. It's just the standard deviation of the difference scores, that's why you have this d here, over the square root of n. So we can call this the standard error of differences. And we're going to put an equal sign because we're doing some math here, and we're going to put the standard deviation over the square root, which is SQRT, of n. And that's 2.56. And we're going to compute our t statistic, which is just the d bar, the average of all the differences, divided by the standard error of the differences. And here we have -1.96. And you can see this is the same value that we have over here. All right, so you're also going to want the p-value, and you can get a 1 and 2-tailed p-value here for your one-tailed p-value, which you're not usually going to use, although you may on the homeworks. You're going to type in an equal sign, and you're going to write out t-dist. X is usually mean, but in this case, for the t-dist function, it's actually talking about the t-stat. So we want to put the t-stat in. Then we need the degrees of freedom, which is n minus 1. So we're going to go to n and say subtract 1. And then our tails, we've got a one-tailed distribution or a two-tailed distribution. So we're going to do 1 first for a one-tailed test. What? So one somewhat annoying thing about using this code is that it requires that your t-stat be the absolute value. So what you can do is in t-stat, in this formula that you have, you're going to put ABS before and after the parentheses, and then put parentheses around the t-stat that you've already got. That's going to make the absolute value of the t-stat, and then this p-value is going to work. Now, to get the two-tailed, all you have to do is change this 1 to a 2 here at the end, and that gives you the two-tailed value. Now, if you followed along this far, I should also tell you that there's a really easy way to do this. You can just type in t.test and go from here. You're going to select your data. The first thing you're going to do is select your data. Once array 1, don't grab the labels this time. Just grab the data. Put in a comma, grab your next set of data over here, put in another comma. We're going to do a two-tailed test this time, but you could easily do a 1 by typing in 1. And then here we've got 3 different types. We've got a paired, a 2-sample equal variance, and a 2-sample unequal variance. So we're going to hit 1 for the paired t-test. And there's the p-value. Now, why did I not show you this first? Because it only gives you the p-value. Because if you're actually doing writing up the results, you're going to need all this other information. Because if you're using it on your exam or on your homework, it's not just going to ask you for the p-value. So you'll need the other information as well. Okay. Now, we need to talk about if you are one of the people that's making a calculator, you also need to know this over here, the independent samples t-test. So of course it's a slightly different formula. We've got mean 1 minus mean 2 instead of just the difference score over here. So we're going to need to find our averages. And then you've got this is called the pooled variance. So you've got the standard deviation here that's squared, which is variance, over the n of both groups. It just so happens that when you have the same n like we do, that just means that you're taking the average of the two standard deviations. So we can do that. But typically, you would actually need to find the pooled variance. Okay, so let's go over here. The first thing we want to do is make our calculator have, let's say, mean species 1, mean species 2. We're going to put an equal sign in there because we're doing some sort of math, and we're going to type in this command and put an open parenthesis. I'm going to take the average of species 1, and we can just slide that over with the fill handle, and now we have the averages for species 1 and species 2. For the numerator in our t-test, it's just the mean of group 1 minus the mean of group 2. And there we go. So next we're going to set up this denominator. Yes, there we go. This denominator category here. And if we go back and take a look at this, what we've got is the square root of the variance for the first group squared over n, which is going to be 20, plus the variance for the second group squared over 20, again, and then the square root of all that. I said that. You don't take the square root twice. Okay, so this is going to be kind of an involved phrase here. We're going to start with an equal sign. And then what we're going to do is we're going to put in SQRT because the main overarching thing that we're doing is taking the square root of this entire phrase. But next, we're going to put in another open parenthesis because we're going to put the squared standard deviation, which is the variance. So we already have the squared standard deviation over n. So the square root of 70.2 over n. Put those together. Then add that to another open parenthesis. This variance divided by this n. Hook those together, close the parentheses for a square root, and now you've got the denominator here. So now we can put in our t value. There we go. This is a lot easier to make. Equal sign, of course, though. We're going to put the numerator over the denominator, and there we've got 1.46, which you can see is the same t-stat that we have here. You can find the tails exactly the way that I showed you for the previous calculator, or you can type in t.test like we did last time, and that'll also spit out the t-value. Okay, that's it for the ANOVA calculator.